Okay, here we have a third example of an optimization question, and it involves a closed rectangular box. And if you read the question, it says a box is to be manufactured such that its width is exactly 3 times its length, which is important. I'll highlight that. And the volume itself is 36 cubic meters. I'll also highlight that. Assuming the box is closed, determine the smallest amount of material needed to construct the box. And when we're talking smallest amount here, we're looking at a minimum. Okay, so we look at here, you look up here, you see width is exactly 3 times its length. So what I've done here is I've let x equal the length here. So this is that term right here, x. And the width is 3 times the length, so I highlighted here, this is your width, and this is the width along here. And for the height, I simply pick y. You could pick L or W, but the height is simply y, which is this variable here. And with any box, the volume is given by length times width times height. So we know that right here, plugging in x, 3x, and y, we get an equation for volume to be volume equals 3x squared times y. A very typical question. Right? And again, the variables we use here, you can use L or W, it's fine. Now, we're also given in the beginning question, I can get rid of all this, that the volume itself is 36. Okay, so that's here. Sorry. That's here. And the volume is 36. So if V is equal to 36, we can let this equation equal 36. And typically you solve for a variable. And again, the idea is to get volume or area or surface area in terms of one variable only. So I solve for y here. Y simply equal to 36 over 3x squared. And you simplify, you've got y is equal to 12x cubed. Okay, so that's basically using the variables x's and y's to set up an equation for surface area. So I'm going to get rid of the color. Now, the surface area is basically the area of all sides. So the area at the bottom is, again, length times width. So it's 3x times x, and there are 2 of these. So that's the area of the bottom right there. The area of a side here, say for example this side right here, is length times width, or height in this case. So it's x times y, and there are 2 sides, of course, which is this side. And finally, there's the front and the back. And it's the area here, 3x times the height here, which is y. And of course, there's 2 of those. So that's the third part of it. So that's the surface area A, if you wish. And if you multiply this through, you'll simply get 6x squared, this term right here, 2xy, and 6xy. So this is your area, and you can combine like terms, so 2xy and 6xy will give you 8xy. That's the surface area in terms of x's and y's. Now what we need to do is to get it in terms of one variable only. And what we can do is simply take our y from here and substitute it in for y here. And when we do that, in this step, we get area is equal to 6x squared plus 8x times 12 over x squared. You cancel x terms here, and you get area as a function of x only is this term right here. And with all, I'll highlight that, with all implicit functions, max optimization functions, you differentiate with respect to x. So you can say dA dx a prime. Of course, derivative of 6x squared is 12x, and derivative of 96 over x is negative 96 over x squared. Next thing we do, again with all these questions, set the derivative equal to 0, which is right here, and we solve for x. You can solve any number of ways here, multiply if you wish, and it works out to be a nice number. X cubed is equal to 8, and our solution is x equals 2. So that really is just about done. 2 things we need to do is we need to verify. So we'll find the second derivative of, I'll get rid of the colors here. We find the second derivative of this function right here, and I like that. Of course, derivative of 12x is 12. Derivative of negative 96 over x squared times this by 2, of course, over 3. It's going to be this term right here, which is positive for all 0 when x is equal to 2, which we know by a second derivative test means it's a minimum. And the final thing that we have to do, I'll get rid of this, is answer the question. It doesn't ask for the dimensions, although it would be 2 by 6x, and you would plug in for y, which would be, in this case, 3. Right? 2 by 6 by 3. But the question asks, what is the smallest amount of material needed to construct a box? So essentially what you can do is plug in 2 here. And that will give us the amount of area, surface area of the box. So I plug 2 in here. The answer is, again, a of 2. You will get 24 plus 48, which is 72. And that is the answer to the question. And we verified it. And it's a pretty standard optimization question.